Odhayan Academy is dedicated to bringing interesting lectures with solved example questions on a variety of subjects with critical concepts. For topic-based worksheets with detailed solutions, go to our website, odhayan.com. If you enjoy our videos, please like, share, and subscribe. In this video, we are going to be discussing question 3 from year 2013, variant 4-2, October-November. The question says that a small metal ball is suspended from a fixed point by means of a string. The ball is given a small displacement and then released. The variation with time t of the displacement x of the ball is shown in figure 3.2. Alright, before we go to the graph where we see the variation of displacement with time, let's understand what was happening during this pendulum motion. This middle line here, we can call this equilibrium point. This was the point at which the ball was originally placed. From its equilibrium position, the ball was displaced towards the right by x meters. This means that before release, the position of the ball, the metal ball suspended by the string, is here. So we can take this to be its starting position. Now let's start analyzing the motion. At time equals to 0 seconds, the metal ball is at the starting position. Then, once released, the ball moves towards the left, meaning it has a displacement towards the left, where it then reaches the equilibrium position again. Now, as the ball approaches equilibrium position, all of its gravitational potential energy converted completely to kinetic energy. So at equilibrium position, we can say that the metal ball has maximum velocity and hence maximum kinetic energy. The ball will then proceed to move further left until it reaches a position like this over here, where all of its kinetic energy is once again converted into gravitational potential energy. So meaning at this point, we can say that velocity equals to 0 meters per second. Once the ball has reached maximum displacement in the opposite direction, the ball again comes back to equilibrium, where all of its gravitational potential energy is converted into kinetic energy, and it again attains maximum kinetic energy and maximum velocity. However, this time the velocity will have a different sign, and we will get to that later once we analyze figure 3.2, the graph. And from equilibrium point, the metal ball will then again come back to its starting position to complete one complete cycle of oscillation. Now let's go to figure 3.2 to understand this motion better. So in figure 3.2, we can see that at time t equals to 0, pendulum has a displacement of minus 1.5 centimeters. If we come back to figure 3.1, we can see that originally, at the beginning, the pendulum was displaced towards the right. From the graph, since the displacement shown is negative, we can say that displacement towards the right is negative, and hence displacement towards the left will be positive. At time t equals to 0, the metal ball was displaced at x centimeters towards the right, causing its displacement to be negative, and then the ball moves towards the left gradually, reaching equilibrium position where its displacement becomes zero because we take our datum point, meaning the point from which we start measuring displacement, to be the equilibrium position. That's why we can say that the displacement becomes zero when the object returns back to this position, the equilibrium position. All right. And at equilibrium position, from the graph, how do we understand that velocity is maximum? Well, we know that the gradient of a displacement time graph, the gradient of a displacement time graph is velocity. If we were to draw a line to represent the gradient at point where the object returns to equilibrium position, we can see that it has the greatest gradient at that time. So this time is t equals to 0.3 seconds. So we can say that at time t equals to 0.3 seconds, the object returns to equilibrium and has maximum velocity. Now the object further moves towards the left to reach maximum displacement towards the left from the equilibrium, and here velocity will be zero. How? Why? Well, here again, let's draw a line to represent the gradient of the graph, and we can see that the gradient of the graph is zero here because it's a straight line. Straight lines have a gradient of zero, and gradient of a displacement time graph is velocity. Hence velocity is also 0 meters per second at time equals to 0.5 seconds. So we can say that the ball reaches maximum displacement in the opposite direction from release from the starting position, time t equals to 0.5 seconds. Gradually from this point, the ball starts moving back towards the equilibrium position in the rightwards direction and reaches equilibrium. Now, when the metal ball reaches equilibrium, it will again have maximum velocity, right? But what about the sign? What about the sign of the velocity? Well, since the object is moving towards the right now, we know that velocity will be negative. Now, how is that understood or represented in the displacement time graph? To understand this, we have to draw another line that represents the gradient at the point where it reaches equilibrium. Here. So here, the gradient is negative. We can see very clearly that the gradient is negative. And since the gradient is negative, velocity will also be negative. Therefore, you see, when an object is in a periodic motion, its movement can be very easily understood from displacement time graph if we know how to find the right ways to understand it by comparing to what the actual scenario suggests. Now finally, from the equilibrium position, object will go back to its starting position, where its displacement from the equilibrium is again minus 1.5 centimeters. Finally reach a velocity of 0 meters per second. It is very important to mention that at time t equals to 0.3 seconds, the velocity of the object is greatest in the positive direction, which is towards the left. And at time 0.7 seconds, here, this point here, t equals to 0.7 seconds, the velocity of the object is also the greatest. However, this time the velocity is just in the opposite direction, in the negative direction, because the object is now moving towards the right, which is the negative direction. So now that we've understood how to read a graph and how to compare it with what is happening in the practical world, let's proceed with the question. Now in the question, we are asked to state 2 times at which the speed of the ball is maximum. We already understood points at which speed of the ball is maximum. So we can say that the speed of the ball is maximum at, oh, I made a mistake. I said that this was 0.7 seconds. This is 0.9 seconds. My mistake. Okay, let's come back to the question. So state 2 times at which the speed of the ball is maximum. Well, we understood that the speed of the ball is maximum at time 0.3 seconds and 0.9 seconds. Now, in the next part, the question asks us to show that the maximum speed of the ball is approximately 0.08 meters per second. There are 2 ways to solve this question. One being using the gradient. However, I would not recommend using the gradient, even though we know that the displacement time graph's gradient is its speed, because it is very difficult to draw the exact gradient of the graph and get the value that they're asking for. So there's another method, method 2, where we use the formula of periodic motion. So we know that velocity, maximum velocity, v naught, is equals to omega x naught, which is maximum displacement. We don't know what omega is, but we know that omega is equals to 2 pi by t. So now we need to find t. On the graph, we can clearly see that t is of 1.2 seconds. So t is equals to 1.2 seconds. So v naught is 2 pi by t x naught, and we know that maximum displacement is of 1.5 centimeters. So maximum speed is 2 pi 1.2 into 1.5 times 10 to the power minus 2, will give me a maximum speed of 0.078 meters per second, which is approximately 0.08 meters per second. Then we write shown. Very simple. See, physics is very easy. A-level physics is very easy if you understand the concepts. Now for part B of this question, the question says that the variation with displacement x of potential energy EP of the oscillation of the ball is shown in figure 3.3. Okay, so at displacement of 0 centimeters, meaning here the ball is at equilibrium, we take its potential energy to be 0, and as the ball gets further away from the equilibrium position, potential energy gradually increases. So let's go to the next part. On axis of figure 3.3, sketch a graph to show the variation with displacement x of kinetic energy of the ball. Okay, simple, very easy. Get back to the graph. So the question says that they want us to draw now the graph that represents kinetic energy change during the ball's motion. We know at equilibrium position, kinetic energy is maximum because velocity is maximum. And as the object gets further away from the equilibrium position, its kinetic energy decreases as all of its kinetic energy is gradually converted into potential energy. This is the graph for kinetic energy with respect to displacement. Now, in the second portion of the question, it says that the amplitude of oscillation reduces over a long period of time. After many oscillations, the amplitude of the oscillation is 0.6 centimeters. Then they say, use figure 3.3 to determine the total energy of the oscillation of the ball for the oscillations of amplitude 0.6 centimeters. Explain your working. All right. From the graph, we can see that at displacement 0.6 centimeter from equilibrium on either side, the potential energy is 4 millijoules. So in a condition and in a situation where energy was lost and oscillation decreases over a certain period of time, we will see that the graph for the gravitational potential energy will not change, but it'll be a bit different. Let's say for a moment in the oscillation at t equals to, I don't know, 0.2 seconds. That's for example, during the loss of the energy, the loss will be such that, let's say, a certain portion of the energy will be lost, but we will observe that at this point in time, the graph, if we plot it, potential energy graph will be this golden portion. For example, it will be this golden portion. It will follow the original graph structure, the same points. It'll just be that a certain amount of energy was lost. You understand? Same for the kinetic energy. We will observe that for that amount of loss, the kinetic energy graph will be very similar. The graph will become somewhat like this. We will see that due to the loss in energy, the amount of displacement that can occur will decrease. There will be less displacement during the oscillation. The only difference will be that a certain portion will be gone. This portion will not be there, and the displacement will be less. So what can we understand from this situation where we were told that due to loss in energy, the displacement, the maximum displacement, meaning the amplitude of the oscillation, decreases to 0.6 centimeters? Well, we can say that now the potential graph will be this much, and this highlighted green portion is the amount of loss of potential energy we've had. We can measure this. This is the amount of potential energy that was lost. And as a result, the kinetic energy graph will change and it will become the red portion. Okay, let me use a different color. Confusing. Let's use blue. This will become the new kinetic energy graph. Our kinetic energy is of 4 millijoules at equilibrium, and hence, after the loss, the maximum potential energy at the two ends or on either side of the equilibrium position during maximum displacement is also 4 millijoules. Now let's solve the question. Using figure 3.3, determine the total energy of the oscillations of the ball for oscillations of amplitude 0.6 centimeters. Explain your working. Okay. Well, there are actually two ways to do this. So first, let's learn method 1. This method can be used for various types of questions, and I'd say that learning this method will help you better understand how formulas work. So first, let's understand method 1. So in method 1, let's start by writing down the formula for total energy of an oscillating object, which will be half m v naught square. It also equals to half m omega x naught whole square. And we know that the total energy of an oscillating object is equals to its maximum kinetic energy, EK. And therefore, we can say that we can analyze the total energy change using the formula for kinetic and maximum kinetic energy. So EK x half m omega x naught whole square. So we can say that EK is directly proportional to x naught square, because in this question we are given displacement and the values of kinetic energy and potential energy. So we need to find a basis or a relationship between them so that we can solve these questions faster and easier. And due to this direct relationship, we can write that kinetic energy 1 by x1 is equals to kinetic energy 2 by x2. Given that mass, this formula can only be used for the same object and this whole concept can only be used for the conditions where mass is constant or when mass of two objects is same, when omega which is angular velocity is constant in the case of one object conditions in two different times, or for or when comparing two objects and their motions. These are the conditions to be able to apply concept that I'm showing here. So since the ball is the same, so we know that mass is the same, and we know that the periodic motion is also the same because they didn't mention if it changed. Since they didn't mention if it changed, we can take it that it's the same. Therefore, we can write for the original motion, the maximum kinetic energy was 25 millijoules, and its maximum displacement was 1.5 centimeters. And now, after loss of energy, since they are still following the same kind of graph shape according to the potential energy, and the mass is the same, and the angular velocity is the same, we can write that now the maximum kinetic energy is x. Let's say, because we want to know what the total energy of the oscillations of the ball for the oscillation at amplitude of 0.6 centimeter is. And we know that maximum kinetic energy is equal to the total energy of the ball. We can do this analysis using maximum kinetic energy concept. So for the maximum kinetic energy, displacement will be 0.6 centimeters here. We can easily find the kinetic energy, and we will get the kinetic energy to be 4 millijoules, which is 4 times 10 to the power minus 3 joules. This is the long method. So instead of doing all of this math for the 2 marks, you can just write in the question, which is method 2, total energy equals maximum kinetic energy, EK max is 0, is 4 millijoules, which we can observe from the graph. Go down a bit. Therefore, total energy at x equals to 0.6 centimeter is 4 millijoules. Method 1 helps to understand how formulas work and how all of this came about. When answering this question, they asked for the energy in joules. We have to write 4 times 10 to the power minus 3 joules instead of 4 millijoules. I hope you have understood everything that was explained. Please check out our website, adhan.com, and you can find the solution videos there.